On Friday, I uploaded on Google Classroom an exercise that will help a better understanding of the Quest algorithm and the extended common filter. So I know that some of the passages are still unclear. Because I mean, it is normal since you need to implement the software in order to fully understand how those two softwares work. And I think that this exercise indeed, it is an important task to do before the homework. So here I didn't provide too much details about the exercise itself. So I only gave you a data file for your MATLAB program. And so you need to upload indeed you need to upload these data.mat on MATLAB, and you will be able to have all the parameters. So let me do that in the on this computer. Since okay, so let me do here. So what you need to do, if you are not so familiar with MATLAB, but I hope you are since you already have done another homework. So you need to take the data.mat.
Scusi, una domanda.
Prego.
Potremmo fare domande circa il chiarimento del testo quando farà l'upload dell'homework? Adesso le faccio un esempio perché faccio questo esempio quando ha caricato questo esempio di esercizio, per esempio non era, io ad esempio ho fatto confusione tra righe e colonne per le misure. Chiarimenti di questo genere si possono chiedere.
Stavo iniziando proprio con questo, proprio per spiegarvi il file.
Okay.
Considerando che l'avevo fatto venerdì sera, volevo proprio spiegarlo adesso.
Niente, grazie.
Ok, comunque se c'è qualcosa di non chiaro, mi faccio subito la domanda così lo spiego.
No, era questo, è risolto, non nessun problema. Era solo per chiedere se poi con l'homework, se qualcosa non fosse chiaro, può essere chiesto tutto qui.
No, ma poi avremo... So the question is regarding the text of the exercise. So the reason why I'm showing that now is indeed to clarify some of the probably details that are not clear from the text. So of course you will be able to ask clarification about this exercise and also of the homework. Few of you start me to send some plots, for example, the quaternion. So what you get from the software. Of course, I'm not able to reply all of you, so don't try to send me all your results because I mean that doesn't work. Of course, you have all now you have everything to solve the exercise. So equations are in the slides. I will also provide you an additional paper that probably could be useful for you. So, but let me start with the text of the exercise. That will be clear in just a moment. So, as I said, what you need to do is to upload this MATLAB file. So the MATLAB file here has 4 metrics. So the first matrix is Q true. So it is the quaternion that I have simulated by using a realistic software. So I'm using, for example, the real data of the baby colon mission. As you can see here, the first 4 columns of this vector are indeed the quaternion at a specific period of the mission. The 5th column only give you the time. So at time 0, I have this quaternion. Since I'm using a time step of 0.1 seconds, so you have 0.1, 0.2, 0.3, and I simulated 10,000 observables. Of course, you can also try to solve for 1,000 if you need. is only to give you the greater part of the data that you can use. But I understand that sometimes probably the software can be slow, and so you can also try to solve for a subset of those data. You don't need to solve for the entire 10,000. The second information that you need. So basically, actually, let's start with the quest algorithm. So what is reported in the exercise test? So as I said, I simulated 10,000 observables with an integration time of 0.1 second. And for the quest algorithm, what you only need to have is the start trigger measurement at that step size. So the other vector that you need to use for the quest algorithm is called OBS. OBS is a three-dimension matrix, so it is a little bit more complicated. But let's do an example. So at the very first epoch, so time 0, so for example, the quaternion through at that epoch will be 1, 2, 4, and the 4.
Vabbè, lo prendo dopo, dai.
So please mute your microphone when you. So the first quaternion will be indeed the first row and the first 4 columns. So this is the first quaternion indeed, because if you look at column number 5, this is time equal to 0. I redo that. So the first quaternion time 0 is the first 4 columns of Q through. This information, you only need to have this information if you want to compare your estimated quaternion with the known one. So since you have the simulation here, you know the true quaternion, okay? Well, so I've said that the OBS matrix, as I said, is simulated by assuming that you have 3 star trackers. And each star tracker at that time give you 2 measurements of 2 independent stars. So we are already assuming that the star tracker has acquired and identified 2 stars per each star tracker. That means that for each time you have 2 stars per each star tracker. So 2 by 3, you have 6 observations. The observations at that time, so the epoch is given by the third dimension of the matrix. So the third dimension here is the time. So for time equal to 0, you have to take the first matrix, submatrix. The matrix is composed, as I said, by a 6 by 7, so let me try to reduce probably. So what you can see here is that for OBS, so at the first epoch, you have a matrix 6 by 7. So the 6 columns corresponds to 6 different observations of the star trackers. The 7 columns are, so the first 3, the vector W, so your measurement. The following columns, so let me, for example, 1, 2, 3, are from the first to the third column, you have the vector W. So what I mean here is that you have WX, WY, and WZ. And that will be the first observation, the second one, the third, the 4, 5, and 6. Okay? Same story. If you want to have V. V is the knowledge of the star position in the star catalog is from 4 to 6. So in this case, you are not going to have here W, but here is V, okay? The 7th column is the sigma. So for, I mean, to simplify a little bit the problem, I didn't give you a sigma given by the error in the acquisition of your measurement, so a sigma W and a sigma V, but the last column of this matrix represents indeed the sigma. You can easily understand that since I assumed that you have star trackers with the same resolution for a simplified test here, I gave you the same sigma. But if you look at the slides here, why you need the sigma? You need the sigma because when you want to determine the coefficients A that you need for the covariance matrix, but also for your BABA problem, you have to use this formula here. However, here is pretty straightforward because, as I said, we are assuming the same sigma. But since it is an exercise in preparation of the homework, I'm not giving you exactly the exact exercise that you're going to have to do homework. So here is only to give you all the information that you need to have a solution of the quest algorithm, and you can compare that one with the one that I show you in the other classroom file, so this one. So here, I think that the structure of the matrix should be pretty clear because I wrote here in detail. The solution that you should have from the quest argument should be very close to this one. Few of you started to do the exercise just after that I uploaded the file on the website, and notice that the initial quaternion that I provided, so this Q through that I provided, had the first 3 columns are the vector part of the quaternion, and originally what I gave you was a negative vector part, a positive vector part. So after a couple of hours on Friday, I updated this file with these values. The reason why the file has been changed is because basically the real quaternions of the quaternions of the real mission has an additional transformation from a real quaternion to its conjugate. So basically, the files that we have for the real mission, instead of giving you directly the quaternion, gives you the conjugate. So it means that the vector part has a change, as a sign change of only the vector part. That's the reason why a few of you notice that in the program that I show you of the quest algorithm, after the solution of the quest argument, there was an inversion of the quaternion. In your case, you don't have to invert the quaternion. So since this is an academic exercise, what I'm doing here is to give you the quaternion that is consistent with the formulation that we have seen during the course. So you don't need to do anything else. Sorry for the misleading part in the beginning, but as I said, since I'm giving you realistic quaternion, I had to consider the fact that there is an additional transformation. This is the only problem. This is the main problem with quaternion, because I understand that many of you has a lot of problems with quaternions because there are different representation. The same problem are amongst the whole community. All the community has to be careful of what is the representation that has been used. Because as I said, I did that mistake because I forgot that the real data were in another representation. The main problem here is that when you use a representation, you always have to be consistent. So don't be, confused. Don't be confused if you see different representation of the quaternions. The important part is that all the representation has to be consistent. So the other part is regarding the Kalman filter that I understand that is still a little bit vague because basically we have seen quickly during the lecture, and so probably for you could be difficult to be implemented right now. But as I said, I will go in detail of that of the solution of this problem by using an extra hour next week. So for the Kalman filter, you need another measurement. The other measurement is given by the quaternion. Be careful that I gave you two vectors. The first one is omega true. So it is the real angular velocity of the quaternion. Sorry, the angular velocity of the spacecraft that is not affected by any error, because basically it's the true of the realistic angular velocity of the spacecraft. The one that you have to use in your Kalman filter is omega measure. So it's the omega measured by the gyroscope. If you do the difference between these two, you can also see what is the bias that I have used, and also you can reconstruct basically the error that the gyroscope has. So this is important because and you can also determine, for example, what is the motion of the spacecraft that I was simulating in my observed data. So the vector that you need is omega measured. The omega measured has n rows, and the number of rows are the number of the time steps, and 3 columns because you have the omega expressed in x, y, and z. So I'm not giving you the lecture of each gyroscope. I'm giving you directly the omega measured by a set of gyroscopes. Okay? So I think that here I gave you the information about the sigma that you should use in your gyroscope, in your Kalman filter. So we have seen a sigma v, a sigma u, that are the standard deviation of eta1 and the standard deviation of eta2. The main problem here, oh sorry, here there is an error, of course. This one is the cross product. So it's the cross product, of course. So I tried to point it out the main issues that I have, basically I got from your question. So the main issues that I think you can have when you're trying to solve for the extended Kalman filter. So the main issue that since a few of you asked me about that, is the propagation of the transition matrix. Well, the propagation of the transition matrix is actually pretty straightforward and even simpler than the transition matrix of the orbit termination, because you have only to propagate two submetrics, theta and psi, that are defined in the slides. And what you need to do here it is. What you need to do, so here f dt is not the same f that you had in your orbit termination. Here f is given by basically these two terms here, omega t, and the additional terms given by the, so basically it's only omega t, basically. So you need to indeed do the cross product of the angular velocity and the vector part of the quaternion. So when you do the transition matrix, when you have to propagate, the Kalman filter, the propagation is within the time step. So if you have the time step from tk minus 1 to tk, you have to propagate the transition matrix from that epoch to tk, basically. So it means that every time that you have to reintegrate your transition matrix, you always start with this initial condition, identity and 0. So let's do an example. We are at the step tk. So we need to propagate the transition matrix from tk minus 1 to tk. In order to do the propagation, you need to propagate by assuming initial condition identity from this matrix and the zero null matrix for this one. You substitute these initial condition in this set of equations. You use OD45, and you can determine at tk, that basically it is 0.1 seconds afterwards, what is your transition matrix that is given by this submatrix here and this submatrix here, because the other two submatrix are fixed, are zero, are null matrix and identity matrix. That will be clear when I will show you the script of the extended Kalman filter slowly, but you can already start to do that. It's not pretty trivial. I mean, it's not pretty complicated. It's basically trivial. So let's do another example. If you have to do from instant tk to instant tk plus 1, you have to restart the integration of transition matrix with these initial conditions. So that's the reason why it's pretty straightforward. The difference between this propagation of the transition matrix with respect to the orbit termination is that you are propagating the error by using the property of the quaternion that the delta error of the quaternion is not a difference between the known and the estimated, but here you have the multiplication. So to have an estimation of the delta quaternion, you have to multiply to have a cross product of the angular velocity and the delta q. So that will be clear when we are going to see, but I saw that few of you already started to implement that. The other main criticality of this problem are the metrics Rk and the Qk. That's the reason why the exercise is pretty helpful, because many of you are not really, I mean, didn't understand completely what I mean with the tuning of the filter, for example. Okay, so the exercise will help you to understand what I mean with the tuning of the filter. So the matrix Rk, for example, can be directly the covariance matrix that you are getting from the Quest algorithm. So since the Quest algorithm only depends on your measurements of the star trackers, and as I said, this is the measurement error covariance, you can directly assume that your Rk is close to the covariance matrix that is resulting from the Quest algorithm. So I jump back to the Quest algorithm solution. What I mean is that the Quest algorithm gives you this covariance matrix. So you can use this information as your initial, as your Rk. I will show you that in the script when we're going to show the solution of the exercise. The other main problem is Q, because I mean many of you said, correctly pointed out what is the value of Q that is reasonable, and this is a fair question. that could be easily, answered for this problem by using the vector. So by using the formal uncertainty sigma v and sigma u. If you use these two coefficients, you're able to, for example, start with a diagonal matrix that you can try different combination of sigma u and sigma v. I will show you the combination that I use when I will show you the exercise. But you can already start to use sigma v and sigma u in order to see how that would affect your Q matrix. As I said, you can also use scale factors in order to see how the behavior of the Kalman filter would change with the values that you have. You don't need to propagate the process noise here. So since you have time steps very short, you don't need to do that. It is a simplified exercise, and it is not requested in this exercise because it is outside the scope of the course. So this is only the presentation of the exercise, but as I said, I will go in detail for next Monday or Tuesday when you want, before giving you the homework. So all your concern and doubts will be completely and fully addressed. But if you still have any problems regarding the text, ask me that probably during the break, or now if you have other problems.
Professore,
Prego.
io ho una domanda, ma quindi i plot che lei ha messo degli estimated quaternion sul testo fanno riferimento ovviamente al coniugato, per il motivo che abbiamo detto? Perché c'è anche...
Non l'ho corretti, giusto? Giusto. Sì, perché non l'ho corretti, vero? Sì, esatto.
Sì, sì.
Sì, ok. Yes. Sorry about that, but this is a nice point here. Since I updated the quaternion file in Google Classroom, I forgot to update the plot here for the quaternion. So what it means that Q1, Q2, and Q3 should be with a negative sign. So I will update that figure. Thanks for pointing this out. That is important indeed. And but anyway, as I said, I mean, this is a good exercise because also show you the problems with representation of quaternions. So you probably think that it is too complicated. But I mean, the problem is that the representation of quaternions always represent a concern because there are different groups that use different representation. So that's the reason why probably could have been a little bit misleading for you to show you many representation. But you have to be aware that there are outside. So when you are going to work on an attitude of the spacecraft, you have to know that you can face that problem. So that's the reason why, I mean, you need to know that. And these exercises show you exactly this problem. So from the academic point of view, the representation that I use is correct. But you can also find other representation that provide the same results, but with different representation of the quaternion. Okay, so let's go back to control theory, because now that probably things are getting a little bit clearer. What we need to do here is to use the knowledge that we have gained regarding the attitude determination and try to accomplish the main task of attitude control and determination. So what we need to do indeed is to control a spacecraft. So the main steps indeed are that you need to determine what is your current status, or your current orientation of the spacecraft. But on the other hand, you also need to use that information to reach or to reach the attitude that you desire. That's the reason why the attitude determination is part of the loop of control schema that we're going to see. Last week we concluded our part on the control theory by only looking at passive stability of the spacecraft. So let me recap briefly what we have seen. So what we have seen is that we started from the Euler equations in general. We assumed the small angle approximation so that we have that the body frame is very close to the orbital frame, and we are assuming also a circular orbit. If we have these two assumptions, we are able to simplify these equations to these three equations in roll, yaw, and pitch. And we have seen that the pitch dynamics for dynamical equation for the attitude control is decoupled from the roll and yaw. So one of your questions, if I remember correctly, was indeed if we have considered the gravity gradient. Well, yes, because as I said, we are considering that our body frame has to move currently with the orbital frame. So if we want that our body frame is going to coincide to the orbital reference frame, what we need to do is basically what we are going to introduce in our equations is the gravity gradient, because basically the gravity gradient means that you have one axis that is always pointing towards Earth. So we have that basically the spacecraft, in particular the Z axis, is going to point nadir pointed. Is going to be nadir pointed. So this ZB should be close to the Z0, so the axis of the orbit. So the the gravity gradient is accounted here, and the terms of the gravity gradient are given by the terms that depends on the mean motion of the spacecraft, as you can imagine, because basically our reference frame is rotating accordingly to the rotation and to the motion of the spacecraft. One of your questions, so we have investigated the pitch dynamical equation. We have seen that it is stable. It provides stability if we choose that the moment of inertia along x is greater than the moment of inertia along the yaw axis. So Ex greater than Ig, so Ix greater than Ig. The main problem also is to investigate the dynamical stability of the rho and yaw axis, because as we have seen, those axes are indeed coupled. So we need to consider this characteristic equation here that comes from the matrix that we have seen last Thursday. Also in this case, as in for the pitch angle, our stability depends only on the gravity gradient. Because one of your questions during the weekend was, but we are considering that there is no disturbance, that's the reason why we're able to have stability. Well, the stability of the system is studied independently from the disturbance now. So we are studying the stability of the associated homogeneous equation. So the system is stable. We have to investigate the stability of the system by assuming that disturbance is equal to 0. But this stability will also be verified when we're going to introduce a disturbance. So let's start indeed by studying only the associated homogeneous. So we need to solve this equation here, the characteristic equation that we have here. You can see that we have has to 4. So we have 4 poles of the equation. One of your questions during the weekend was indeed, but why we need to have an imaginary number since I mean, usually the stability is obtained by having a negative real part of the pole of the solution. Well, this is cannot be the case here, because as you can see, we have that the solution of this equation is given by s squared divided by omega 0 squared. So it means that exist two solutions, S1 and S2, and their complex conjugate. So indeed, it will be minus. So it will be S1 and S2. So also minus S1 and minus S2 are solution of the equation if these. So if S squared is not negative. So if S squared is positive, you will have these two sets of solutions. And so there is no way to have a positive, to have a only negative real part of the solution. So you can't, from here, you can understand that you can't have asymptotic stability of the system by only using gravity gradient. That's the reason why the only way to have stability for the roll and yaw axis is to have that both these numbers are negative, and so S squared is negative, and so S will be indeed a complex conjugate, will have a complex conjugate formulation, solution. So what you need to do here is so what you need to do here is to verify three different conditions in order to have that this S squared is indeed negative. And we have seen that these three conditions here result in different regions of our sigma x and sigma z plane. So we have seen that the first condition, this one, give you that all the solution inside this parabola here cannot provide stability. So we have to exclude this one here. So let's do it like that. So this part here has to be deleted because basically are do not satisfy this condition here. The other condition is that you are not able to have solution from the second and the fourth quadrant because sigma x times sigma z is negative. So the only two parts in which you can have this solution are these two, because also you have a third condition that sigma z it should be less than sigma x. And so all the points above this line here cannot provide stability. So the stability of the system only depends on these sigma parameters that are function of the inertia, moment of inertia of the spacecraft. So the moment of inertia of the spacecraft are function of, so these sigma are then a function of Iy, Ix, and Iz. So from the pitch stability, we know that we want that Ix has to be greater than Iz. But also, we know by using in this region here, we can verify that also the moment of inertia of the pitch axis should be greater than the other two. Is that you have an opposite condition in this very small Debra-Delp region here, B, in which you have that Iy should be the lowest moment of inertia. The other important thing here is that Iy should be less than Yx plus Iz. So this condition here is given by the fact that sigma z has to be less than 1. Okay, so let's try to quantify this important information. So last week we have seen 2 examples, and the example that we have seen is that the spacecraft has moment of inertia Ix, Iy, and Iz of these quantities, and we can use a boom in the z direction in order to augment these moment of inertia Ix and Iy. So what we can see here is that by augmenting this moment of inertia, we have seen from the MATLAB script that I showed you last time that you will have 2 different conditions. So by including and by starting from an angle, a yaw angle equal to 5, what you can see here. So this is not what we. This is the first case. Let me see. So if we start with the angle psi, so the yaw angle equal to 5, what you can see here is that the red curve represents your oscillation of the angle in the roll, pitch, and yaw axis, and you can see that the oscillation along the roll axis are larger if you have a lower moment of inertia. So by including a boom, you are able to increase the moment of inertia and basically to reduce the oscillation along the roll axis. What we want to do in the next hour is to use the first actuators for the course, in which we're going to indeed remove or dump the oscillation that we have seen so far. So we know that the gravity gradient cannot provide asymptotic stability, but can provide stability in roll and pitch and yaw axis if the conditions of the moment of inertia are satisfied. We need to include actuators that, for example, enables the damping of those oscillations. So the first case that we are going to see is indeed the libration control by using wheel dampers. And the second actuators that we are going to see also, it is the magneto-Torqrods. So the wheel dampers, as we are going to see, have the possibility only to dump the oscillation of the spacecraft. So can work properly by the combination of the gravity gradient that has to provide stability to the system through a certain configuration of the moment of inertia. But you also include an extra term given by the wheels in order to dump those effects. And what you're going to see indeed is that we can provide a certain configuration to dump those oscillations. We are going to see that, for example, especially for the pitch axis, because as we have seen, the pitch axis is decoupled from the other two, and we can use a damper in that axis in order to not only have stability, but to approach asymptotic stability to a certain angle that we're going to see will not be, for example, our desired angle, but is an angle that depends on the disturbance that is acting on the spacecraft. So let's have a break here, and we're going to start with the dynamical, so the evolution of the dynamics in the pitch axis with only the gravity gradient, and we're going to introduce the wheel dampers in order to show how those act on the stability of the system. In the meantime, we can discuss about, I mean, if you have any questions regarding the exercise or this part of the course. Okay, so there is a question regarding the tuning of the Kalman filter. So as I said, this exercise is, so the exercise that I gave you doesn't show you many differences in the tuning of the filter, because as I said, I tried to give you a simplified example. So what you should expect, indeed, is that if you, so the process noise, let me show you from the slides, probably it is better. So the process noise here is giving, basically adding some information to the covariance matrix that you are propagating in in your Kalman filter. So if you have larger values, it means that basically you are assuming that your basically data from the gyroscope are affected by significant errors. Because the problem here is that when we are propagating the covariance matrix, we are not including the matrix G. So the only information that is given by the mismodeling of the spin rate measurements given by the gyroscopes is given by the matrix Q. So if you increase the matrix Q, what it means that you are deweighting your gyroscopes. So what you could expect, for example, let me show you from this one, that this curve here, so the sigma in the angle, you can see already a result that I show you in this exercise, that the first thing that you can notice is that the uncertainty with the extended Kalman field is larger with respect to the Quest algorithm. So that should be a very strong surprise, because what I gave you is a very poor gyroscope. So it means that when you try to determine the attitude of the spacecraft, you are introducing an error that is larger, significantly larger than the star triggers. And the star triggers are not able to correct that because it is too large, and so your estimation tends to increase over time. In principle, you use gyroscopes to decrease this curve here. So usually the sensitivity of, so the precision of the gyroscopes that you find is definitely better than what I gave you. So that's the reason why here the tuning could not work properly, because basically the information provided by the gyroscope is so poor that you are not able to increase or reduce a Q in order to overweight your gyroscope measurements. You are definitely, so the value of sigma V and sigma U are indeed too poor, so low quality of the gyroscopes, so that you're not able to scale Q in different ways. But assuming that here you have other values, so for example, here you have 10 to the minus 11 and 10 to the minus 10, Well, in that case, the weight of Q would change significantly the curve here, so the sigma that you have in the extended Kalman filter, because what you would have is that the sigma will be lower compared to the extended Kalman, to the Quest algorithm. And so you have to be careful that your error is not going to be outside the sigmas. So in that case, you scale your Q in order to be sure that you are not overweighting your gyroscope measurements. So in the case that you have here, I can understand that you cannot see really the difference, because sigma V and sigma U are so large compared to the precision of the star triggers that I gave you. But in principle, if you have better, we can try to, for example, during the exercise next week, to change the simulated measurements of the gyroscope and see better how the tuning works, because probably that would be pretty helpful, and we'll show you what I mean here. But basically, the main point here is that the tuning is indeed directly related to the gyroscope precision and to the star trigger precision. So if you have the gyroscope so poor, so low quality, that the tuning could not be changed dramatically. If you have the gyroscope provide you a good information, in that case, the tuning will be fundamental, because you can indeed go to have a divergence, or on the other hand, you are downweighting your gyroscope measurements, and so the measurements that you're getting from the extended Kalman filter are not so different compared to the Quest algorithm. But as I said, those should be showed using the script next week. That would be helpful, I guess. Yeah. Okay, so the main purpose here now is to introduce control actuators. So we have seen that gravity gradient only provide stability for roll, pitch, and yaw axis for specific configuration of the moment of inertia. But we have structural problems to do that. For example, we have seen that the moment of inertia so the moment of inertia Iy has to be less than the sum of Ix plus I zeta. And we know also that Iy to be in the first region, the region A, should be so in the case that we have seen before, so in which we had that Iy is equal to 8, Ix is equal to 6, and Iz is equal to 4, we used a Z boom, so a boom along the yaw axis in order to... Prego.
Scusi se la interrompo, potrebbe mettere in modalità presentazione che si vede più grande, per favore?
Sì, sì, certo.
Grazie.
Prego. Provo a scrivere anche più grande. Ok. So, so these Ix, Iy, Iz, so Iy equal to 8 are the cases that we have seen before. I don't see my mouse anymore. So let me see. Okay. So it's basically this example here. So we have used a zoom, a boom along the z-axis in order to augment Ix and Iy. The problem that we have seen here is that we are not able to increase that with values that are completely unconstrained, because indeed we need to that these two relationships are satisfied. So for example, if we want to augment AD, so Iy to 82, for example, so Iy equal to 82, and Ix, so basically we have to be careful that Ix plus Iz has to be greater than that. So we have, we know that Iy has to be larger than these two. But in order to have that this condition is satisfied, we need to include, so to have at least that Ix is b equal to 82, 82 minus Iz that is equal to 4. So basically, Ix has to be between 82 and 78. That's the reason why when we did the zoom, the z-boom along the y-axis, Ix was equal to 80. So that shows you that basically we are not able to provide unconstrained solution of the problem with the moment of inertia only. So we need to include additional actuators in order to control the system. Okay, so let's start with okay. By using the pitch axis. So we want to determine the dynamical equations along the pitch axis, since we know that the terms that are given by the pitch dynamics are theta dot times the moment of inertia along the pitch axis plus the terms given related to the gravity gradient, so 3 omega 0 squared times the different Ix minus Iz that, as we know, has to be greater than 0 in order to have stability. And that is equal to a generic disturbance along the axis. So by looking at the MATLAB program, so let's assume, for example, to have a disturbance along the pitch axis of 10 to the minus 5 Newton per meter. No pitch, yaw, and roll angles, initial angles. So if we simulate that for example, a few hours, let's do, okay. So now let's look at only to the black curve in which we have the boom along the z-axis. Okay, so what you can see here is that the yaw and roll axes are not moving because the disturbance, it is only along the pitch axis. And we see that we don't have an oscillation along the we don't have an oscillation with a mean value equal to 0, but we have that the spacecraft is going to oscillate because of the disturbance along the pitch axis with a certain amplitude. And also what we can see it is that we have only stability because this perturbation is not damped. So we are only able to have that. Let me try to have the slides. So what we have here, let me know if it is too small, but what I would like to show you here is that this is the pitch dynamics. So now we introduce a constant torque along the z-axis that is equal to 10 to the minus 5 Newton per meter. So the spacecraft tends to oscillate with this value. And I mean, I forgot to write an important term here. So this is theta. Why it is important to have theta here? Because we can indeed determine what is the value at which, the mean value at which this dynamical equation is going to have a mean value. Because as you can see here, the theta direction is oscillating along, for example, an angle equal to 2.5 degrees. This 2.5 degrees is not an angle, a random angle, but is given by the value of the torque and the spin rate of, so the spin motion, the mean motion of the spacecraft, and the difference of the moment of inertia along x and z. So basically, what you can compute here, you can compute the steady state value that will be indeed T dy divided by 3 times omega. Let me see, it's called omega 0 squared times Ix minus Iz. And that gives you, so let's do in degrees. So it is equal to 88.62 degrees if we use the old moment of inertia. So the moment of inertia 6 and 8 and 4. But if you use the moment of inertia that I show you for this plot here, that are given by 80 and 82, Ix will be equal to 80, and this one will be equal to 4. And you can find indeed that this system is going to oscillate between an angle of 2.3 degrees. And this is only given by the gravity gradient. So the gravity gradient is counteracting to the disturbance and providing an oscillation of the system. Well, what we want to do here is to introduce an actuator so that includes an additional term that is the damping. So the damping of the system is introduced by using a so-called wheel damper. So basically, we have, so if this is the spacecraft, so you will have a wheel into an armature here. This is the armature of the wheel. You have the wheel here. That is, so within the armature, you have a fluid with a certain viscosity. So it means that if the spacecraft starts to rotate along these axes, so this is the spacecraft is seen from the X and Y. So this is the X and the Z plane. So basically the orthonormal, so the normal axis of this plane is your pitch axis. So you are seeing the wheel from above. So if you have a disturbance T dy of 10 to constant disturbance, what happened here is that the spacecraft is started to rotate. The wheel is still, but since there is viscosity in these in the armature, the wheel starts to rotate following the rotation of the spacecraft. But what happened here is that the viscous fluid creates a sort of torque that is going to slow down the wheel itself, or basically it is going to slow down the spacecraft, giving a counter-react torque that is going to dump the effect induced by the disturbance itself. So basically what happened here, starting from 0, the wheel is still, but the spacecraft is start to rotate because of the disturbance. So the viscosity is going to transfer some of the energy to the wheel and dissipate this energy to the viscosity of the wheel. This dissipation, indeed, is responsible to provide a torque that is going to counter-react the torque that is given by the disturbance itself. So that's the reason why you have to add an additional equation here. So you have that your wheel will have a certain moment of inertia. You have the angular velocity, so the angular variation of the angular velocity of the wheel, so the acceleration of the velocity of the wheel, that is given by the viscosity of the so this is the viscosity is given by the viscosity of the fluid, and it is a damping coefficient that multiplies the difference between the angular velocity of the spacecraft in the z direction, in the pitch direction, so this will be theta dot, and the angular velocity of the wheel. So when you will have that the two will be exactly opposite, the wheel will not have any additional acceleration. So it means that, as I said, it is going to generate a torque only if you have a differential rotation between the armature, so the spacecraft, and the wheel itself. So it means that when you're starting from the wheel that is still and the spacecraft is going to rotate, this rotation is going to induce a torque on a wheel that will be given exactly to the so basically, in order to write that in this equation here, let me see if I can erase that. Okay, I'm not able to erase that. But what I mean here is that this equation here, so let's write that here. You can see that the same torque is going to be opposite to the disturbance. So the differential rotation between the spacecraft and the wheel is going to counter-react the disturbance that you have on the pitch axis. Okay, but now we are going to see that in the script that I show you before. you can also analyze the problem by using the Laplace transform. Why it is useful to do that? In order to determine what we already seen previously when we had only the disturbance and not a viscous, a wheel dampers that is acting on the spacecraft. So if you write in terms of the Laplace transform, you can find easily that the differential equations becomes to this algebraic formulation. And you have this matrix here that multiplies the angles of the spacecraft and the angular variation, angular speed of the wheel. You compute the characteristic equation of this matrix in order to determine the determinant when it is equal to 0. Because basically what you need to do, you will need to invert the system. So basically you will have the delta S is indeed the characteristic equation of this matrix here, or is the determinant basically, okay? So what we need to do here is that in the Laplace domain, we're able to write the disturbance in terms of variation of the angles. Be careful that when you write the disturbance in terms of the Laplace transform, when you have a step function, as we have seen here, step function means that at a certain time, the disturbance was 0 before, but is coming to be a certain value. So this is the time. At a certain time will be indeed equal to dy, t dy. So at a certain time, for example, t0, you have a constant. After a certain time, you have a disturbance that is constant. This in the Laplace domain, this step function is indeed, so t ds in this is in the Laplace domain is given, is divided by s. That's the reason why you have t dy divided by s. So basically the disturbance expressed in the time domain is converted in the Laplace transform by dividing by s. So this t dy is the disturbance in the Laplace domain. Why it is useful to do that? Because if you invert this matrix here, you are able to determine a direct relationship between the variation of the angle of the spacecraft and the disturbance itself. So assuming that the spacecraft, as I said, is starting from initial position equal to 0, initial velocity equal to 0, what you get, indeed, is that the theta steady state is the limit of this function when s tends to 0. Be careful that when you want that the time is going to infinite, so to the correspondent transformation, so the function of time at infinite time, corresponds to a limit of the function in the Laplace domain when s tends to 0. That's the reason why s is tending to 0, because now we are trying to have the value of theta at infinity time. So, and you have to multiply this function by s. So there is also an extra s here. These are always a problem. Are related to the Laplace transform definition. So if you multiply that by s, you can easily see that these two terms, so these two s will be simplified, and this term tends to 0. So you will have that the theta ss will be converging to the value that I showed you before. So the gravity gradient and the wheel dampers are not going to give you the desired angle that you want, but it is going to converge to a value that directly depends on the disturbance and the moment of inertia and the mean motion of the spacecraft. So although you're including an actuator, this actuator is only going to dump your oscillation, but it's not going to provide the orientation that you want. Okay, so let's do that in the, so that's the case in which the gravity gradient is only acting to, counter-reacting to a disturbance 10 to the minus 5. So now let's try do the same. Let's keep this figure here by including a wheel damper. So the wheel damper here, so the wheel damper, and let me use comment, the same moment of inertia. So figure 2. So now I introduce a wheel damper with the moment of inertia equal to 0.4 kilogram per square meter and a coefficient d equal to 10 to the minus 3. So let's see what happened here. Okay, he closes my figure. So let me redo. So in order to compare exactly what we had before. Okay, so what you can see here, so the time here is in hours. Okay. Okay, so let me. So the red one will be the figure without without the. So the black one will be without the damping. Okay, here it is. So, but like this will not be visible. So let me try to zoom in. Okay, so what you can see here is that the black one, it is the gravity gradient acting on the spacecraft that, as we have seen before, only provides oscillation between 0 and almost 5 degrees because the mean value is 2.3 degrees. You can see that if we have this gravity gradient for 150 hours, so basically we have for 5 days, what we're going to have is indeed that the spacecraft is going to oscillate with a certain spin rate. What you can see here is that if we introduce a damping, the spacecraft is going to indeed have similar oscillation with the same rate. For example, let's see if I can zoom here. But the amplitude is definitely lower because the damping is acting on the spacecraft, and the damper is reducing the oscillation, but the mean value of our orientation is still always close to 2.33. So the wheel dampers are not able to provide any control on your final desired angle because this one is only given by the disturbance, the mean motion of the spacecraft, and the moment of inertia. So the example that I showed you before is indeed by using the moment of inertia Ix equal to 80 and Iy equal to 82. And that's it is in the example that you have here. If you want to try with smaller moment of inertia, you will have exactly the same behavior, but the final steady state angle, instead of be 2 degrees, will be equal to 89 degrees. So it is a very large angle. The value that I have used for this plot that you can find here is assuming some possible realistic characteristics of the wheel. So in principle, what you can do is that, okay, but why we don't use, for example, a damping factor that instead of be 10 to the minus 3, it is definitely larger than that, in order to overdamp the for example, 3. That will only depend on the viscosity of the system. So, for example, if you increase D, you are going to have a larger, so a lower variation of a lower variation of the amplitude. So if you want to go lower, so for example, 3 10 to the minus 4, you need to have some viscosity of the fluid that are going to change drastically your behavior. So the problem here is that you're not able to provide different sets of D and the moment of inertia of the wheel randomly, but the viscosity of the fluid is given by the property of the fluid, and the moment of inertia of the wheel cannot be so large, because if the moment of inertia of the wheel is large, it means that also the wheel is large itself. And so you can have indeed problems in terms of mass of the spacecraft. You want to always have, for example, a 0.4, a moment of inertia that is close to 0.4, for example. So you have to be careful that these values cannot be chosen randomly, but for the wheel dampers are directly related to the wheel characteristics and properties.
Mi scusi, prof.
Prego, prego.
Può ripetere cosa non prevede la wheel?
Si riferisce al fatto di raggiungere il valore medio o della viscosity o del momento di inerzia?
No, del valore medio.
Ah, okay. So the main problem with the wheel dampers is that our actuators, so the question is regarding what are the main weakness of the wheel damper. So the main weakness of the wheel damper is that it can give you so a smaller variation of the pitch angle, because basically the damping factor is going to reduce the oscillation after a certain time. But the main problem is indeed that the steady state, so the final angle at infinite time at which the spacecraft is going to converge, is not, for example, equal to 0, that could be our goal, but will be only related to the disturbance and the spin, the mean motion of the spacecraft at the moment of inertia of the spacecraft itself. So it means that the wheel dampers are not well suited to obtain our desired altitude. But we have to design the spacecraft in order to reduce, for example, the steady state angle. We can increase even further the moment of inertia along X, for example. But as I said, you are not able to change Ix without changing Iy. And so the configuration of the spacecraft, if you increase the moment of inertia, will require larger masses and complication in the properties. So the wheel dampers, from this point of view, are not really the best actuator, and that's the reason why are not really used right now. So historically, have played an important role because, of course, enable the stability of the spacecraft by using the gravity gradient and this simple device. But if we want to determine the attitude of the spacecraft, we need additional actuators, and that's the reason why what we're going to see next are the magnetotorques and the thrusters and the reaction wheels. Reaction wheels are not related to the wheel dampers. In the main principle of the reaction wheels is to provide a rotation of the wheel itself that is going to create an angular moment of an angular moment that is transferred directly to the spacecraft itself. So the device of the reaction wheels are going to increase the angular velocity of a wheel that is not included in an armature with the fluid, but is an inertial wheel in which basically the only principle is to increase its speed, and the torque that is used to increase its speed is used to counteract the torque given by a certain perturbation. That will be significantly different because we are going to modify the velocity of the wheel in order to counteract the disturbance. What you can see here is that we don't have any control on the wheel. The wheel is going to change its velocity because of the viscosity of the fluid that is acting because of the angular velocity along the pitch axis. So it is an inverse problem here. And when we are going to see the reaction wheels, it will be clear that we need an active actuator that is going to modify, for example, its velocity in order to counteract a force. So the other actuator that we can use to determine to mitigate the oscillations or to dump the oscillation induced by the gravity gradient are the magnetotorques, also called Torqrods. So the principle here is to use another property of the Earth. So for the gravity gradient, we use the gravity of the planet in order to stabilize our spacecraft. Here we use the magnetic field to determine a torque that is going to counteract a specific disturbance. How we can use the magnetic field of the Earth to counteract the torque? Well, what we can do here is to determine, is to create the three different coils that will have a specific intensity, current intensity, that are going to generate another magnetic field. So each coil that will be, for example, placed, let me show you what I mean. So if this is the body reference frame, it is a really simplified scheme, but assume that you have a coil here, another coil here, another coil here. So if you have a current that is going, actually this direction, for the three coils, you are going to generate three magnetic moments, mx, my, and mz. Well, you know that you will have, this is the body frame of the spacecraft, assuming that the body frame is, very close to the orbital reference frame. And you know that the magnetic field of the Earth has a certain direction. For example, let's write here, this is B. Well, what you can do is indeed try to do the cross product of the moment of inertia of the magnetic field of the Earth and the magnetic moments of the three coils. So what you want to do here is to determine which is the torque that results from the cross product of the magnetic moment of the three different coils and the magnetic field. What you can see here is that this matrix, that is well known, can be written with the antisymmetric skew matrix, in which you have a zero diagonal, bz minus by bx, that multiply the vector of the moment of the magnetic moment. So the first question is, are you able to provide a control torque on the spacecraft that is given directly by a certain configuration of the magnetic moment? So for example, the magnetic moment is directly given by the current. So you can change your intensity of the current in the coils in order to determine which is the mx, my, mz, if you knew the magnetic field of the Earth, so the direction of the magnetic field. However, you are not able, you can't indeed determine the inverse of this matrix, because you know that this matrix has a rank equal to 2, so you're not able to invert this matrix. So the answer to this question is no. You are not able to provide a torque vector, a control torque vector that is given by the cross product of the magnetic field of the Earth and the magnetic moment of the three coils. There is, I mean, any important remark on that, because the main reason you are not able to provide a torque that is indeed a control torque, a generic control torque from these three magnetic coils, because you are not able to provide a torque along this direction. Since the torque is always orthogonal to this vector here, you are not able to provide any control torque along the vector of the magnetic field. Okay, so we need to, and we are going to conclude with that, to find a strategy to use the magnetic coil to, for example, reduce the to try to reduce the yaw axis rotation. You have to be careful indeed. So far, we have seen that the yaw axis is poorly controlled by the gravity gradient. We have seen indeed that when we have done for example, we included a disturbance torque on the direction of the psi angle, so the yaw axis. We have seen that the psi angle is going to reach unreasonable values because basically the gravity gradient is not able to counteract the disturbance, and that's the reason why you need to include the full dynamical equations, so the correct dynamical equations of the spacecraft attitude, in order to determine the spacecraft attitude control. So the main problem here is that we need to use additional auxiliary actuators in order to control psi, although you have the gravity gradient. Well, we're going to see tomorrow that we can try to determine a control torque along the y-axis using the Torqrods that can mitigate errors induced by a disturbance along the y-axis. So tomorrow we're going to see that, and also the fact that we are not able to provide a control scheme with the Torqrods that is completely decoupled between the yaw and the pitch axis. By looking briefly to this product here, you can see that in order to have the torque along the yaw axis, you need to do m zeta times by. But if you have b zeta, if you have m zeta, so a current along this coil here, you have also an underside torque on the pitch axis given by bx times m zeta. So you have to be careful that your control that you're acting on the yaw axis is also going to change your pitch dynamics. So I'm stopping here, and tomorrow we are going to restart from the Torqrods and provide you some example using a MATLAB script that show you the benefits and the weakness of the magnetic Torqrods. Because afterwards you're going to see the reason why thrusters and reaction wheels represents the main devices that enables a good control, active control of the spacecraft.